Okay, we've had a look at interference in water waves when we've got water waves coming from two sources. Now we take those same ideas and apply them to interference of light. So we're looking now at two-source interference of light, also known as Young's double slit experiment. All right, so here's a general description of the situation which I want you to put into your notes, and also this diagram can be printed off and put into your notes as well. So we've got a single slit here. I'll talk about the reason for the single slit after another few slides. We have a single slit here, but over here, more importantly, we have a double slit. And we have light waves being diffracted coming from one slit and diffracted coming from the second slit, and in exactly the same way that water waves interfere, producing either constructive or destructive interference. Then we get interference of the light waves, once again giving us constructive or destructive interference. So we get a series of what are sometimes known as fringes occurring, and that's referring to what we're seeing on this diagram here. Right in the middle, we see a bright bit of light. That corresponds to that central maximum that we got with our water waves. And then over here, we get another bright bit of light, and on the other side, similarly bright light there. Those correspond to our n equals 1 maxima, our first order maxima, where the waves traveling from one source compared to the waves traveling from the other source travel one extra wavelength. So the waves traveling from this source travel an extra wavelength to get here, and we get constructive interference occurring. In between, that area there, that is going to be our first order minimum, where waves traveling from one source travel an extra half length compared to the other, and so we get destructive interference there, or cancellation occurring. All right, so notes, diagram into your books. Here's another diagram. Now I've given you this one, so you don't have to print it off. You've already got it, but it really shows the same sort of situation. So again, here's our double slit, and here is, with these things labeled a little bit more, our central maximum bright, our dark, which is our first order minimum, then our first order maximum, second order minimum, second order maximum, and so on. And we've got down the bottom here intensity of light on the screen. So we've got bright, 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 dark, dark, dark. Okay, so that's just another diagram illustrating slightly differently what we saw in the first one. Take note, monochromatic. Now you've written the definition of monochromatic in your notes already. So the question is, why do we have to have a monochromatic light source? Well, if we just pop back to the diagram again, the pattern that we're seeing over here on the right-hand side, this pattern that we're getting over here, would be formed for one particular wavelength or one particular color. If we use a different wavelength, then we would get our maxima and our minima forming at different places. So instead of there being a nice, neat pattern, what you would see is effectively all the colors of the spectrum. So you'd get a sort of a little bit of a jumbled spectrum being produced if you used white light consisting of many colors. So if you want to see a nice, clear pattern, you use monochromatic. All right, so I think you should write something in your notes about that. So what could we write down? We could say, if only one wavelength or color is used, then a clear pattern of maxima and minima is produced. White light would produce a pattern of overlapping colors. Okay, the other question that we want to ask is, why do we need to have this single slit here? Here's our double slit. This is the part that's producing the whole interference type thing. So why do we need a single slit in the first place? Okay, now this is something that's only necessary with certain types of light sources. Right? Now, one of the things that we have discussed is the need for the light source to be coherent. Now, if you're using a light source like this, the light coming from that light source would not be coherent. So if you pass the light from this light source here through the single slit, then you get diffraction occurring from there, and that acts like then a single source. So by having a single slit, we're able to take what light that is not coherent and effectively produce coherent light source appearing to come from a single source. So I think the thing we need to write in our notes would be just a statement that the single slit acts as a point source producing coherent light. Okay, back to the diagram we had before. I want you to add some extra labels to this diagram, because if we're going to use Young's experiment to measure the wavelength of light, we're going to have to know certain measurements. And the particular measurements that we're going to want to know is this distance here. That's from the center of that slit to the center of that slit there. So that distance is given the symbol little a. We also need to know the distance between the slits and the screen. And the third thing we want to know is the distance from one maximum to the next maximum, and that's given the symbol little x. So if you can add those three labels to the previous diagram that you've got, we'll have a look in a moment then as to how we use those three measurements to work out the wavelength of light. And there's our formula there. Now, I'm just pulling this formula out of thin air at this stage. I can show you later on where the formula comes from, but it is a formula based on a particular little approximation, which again I will explain in class. So if we want to work out the wavelength of light, we take those three measurements and we do the calculation. So I want you to, in your notes, write down that statement and the formula, and then we'll write in words what those three symbols A, X, and D stand for. So A is slit separation, and that's measured center to center. X is distance between adjacent maxima. and D is distance from slits to screen. All right, okay, just something else to note. We talked about using a single slit to produce coherent light. If we were to use a laser instead, then a laser automatically produces both monochromatic, one color, one wavelength, and also coherent light. And that's what we'll use in the class to perform Young's experiment and to take measurements so that we can calculate the wavelength of the light being produced by the laser. But just to give you a little bit of practice first of all yourselves, I'd like you to copy out this example here and do this example in your notes. So the first part involves you calculating not the wavelength, you're given the wavelength, but it involves you calculating the fringe separations. That, in other words, is the distance between two adjacent maxima, the x value. And the second part's quite important. This is pretty common sort of thing that pops up in exams, both in multi-choice and in long answer questions, stating what sort of effect things are going to happen if you make changes to the setup. Changing, for example, it says here the slit separation, changing the intensity of the light. Those are a couple of possibilities there of things that could be changed. So give that some careful thought because you are going to be tested on that sort of detail. Okay, as I said, we'll do Young's experiment in class tomorrow also, and measure the wavelength of laser light.